I guess doing a second midterm for machine design.
Yeah, he said that we're not gonna have the time for our project. Because we did do the term of, like April, technically 2 weeks of weeks. And then it's like, oh, you're not gonna have time for the project, so. Here's my other project. Second term.
I'd be waiting for them. Really happy. They don't have this little stuff.
He said like 40% of your
Yeah.
Now the thing too, you talk about the ascent curve. Because you guys do not listen. So like so we're gonna give like every material.
Yeah.
So if you're trying to like the fatigue light, especially in the load, then your ascent curve matters. Like a lot. And I told him, it's like, we couldn't see it. It's like, you're using the wrong. Yeah, 15 minutes. Oh,
yeah.
Yeah, and we had the same argument again today about it. And it's just like, you know what? At this point, like, I'm not going to convince you, but just ask Dr. Park and he will literally explain to you.
Maybe they just need to hear from authority.
Probably. Yes. A little bit. Yes.
I need that.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Beautiful day. We've had our weather. The weather's been great after being really cold and then really hot, and then now it feels like it's stable. Okay, so today, first thing today, I totally forgot. So first thing we're going to discuss today is kind of just the very end of our open foam activity that we didn't get to last time. So we finished everything with the activity, but I did want to go over some of the exercises I want you to do at the end. So we'll go through that first thing today. And then after that, we are back on discussing theory. So this is the last, I would say, kind of major section that we have in this class. This is the last section that I'm going to test you on for the midterm. So midterm 2, remember, is 2 weeks from now. So it is on April 22nd, which is a Wednesday. And the last section that we're going to go over in that is time marching. So we're going to start to go over that today. That's basically going to cover our next 3 lectures. And then, we'll finish it out from there. So after the second midterm, there's really no more theory to cover at that point. It's really just kind of practicing with open foam and talking about kind of practical implementation, tips and details for running CFD. So this is kind of the last, hopefully the last section where you'll be kind of taking notes and we're looking at equations, things like that. Okay. Okay. All right, and then there is one more homework assignment that I want you to do with regards to time marching as well. So that will be posted early next week, just because I know that you guys are still working on homework 4 right now with the restricts. Okay. All right. Any questions about anything before we get started for today? Okay. All right. So let's hop back into the activity. Okay. All right. So this is our activity that we did on Monday, right? So we were simulating flow in this channel with the pocketage, right? So we basically got through everything with defining the mesh and block mesh dictionary. We defined all the patches and all that good stuff. Okay. So I would say the part that we didn't really get to cover all too much, or the part that we kind of rush at the end, was the specification of the boundary conditions. Okay. So this part, you know, I don't have too much written here, just because it's not too difficult. The only thing you just have to make sure is that you know, that you first of all make sure that you're running in a laminar form, and that way you can delete all of the other variables that are associated with the turbulence. And then when you're setting these boundary conditions, make sure you have a section for each of the patches that you defined, right? So remember, we have 4 patches that we defined for our model. We had our inlet patch, we had our outlet patch, we had all the fixed walls, and then we had the special front and back faces as well. So make sure you define boundary conditions on all 4 of those faces. Okay, and all of the you know, all of the types of boundary conditions kind of follow this format. Okay. Okay. All right. After that, you'll be able to run the simulation using the foam run command, just like in activity 1. And then you can view the results. Okay. Okay. So before we kind of move on, you know, I did want to go through kind of the last 3, or the 3 problems that I want you to do for this activity. Okay. So problem 1 here is short answer questions. Their part A is actually quite involved. That's the one I kind of want to describe. Part B is to you know, or problem 2 here, I want you to do some additional post-processing. And then problem 3, we're going to do something called a mesh convergence test, which we'll explain in a bit. Okay. Okay, so let's talk about problem 1 first. So if you read problem 1A, right, what I want you to do for problem 1A is to basically describe in words what your results are showing. Okay. So this is an important skill whenever you're doing any kind of simulation work. So whether it be finite elements, whether it be CFD, what have you, right? So there will always come a point where you're going to take your simulation results and you're going to have to present it to other people, traditionally in the form of some kind of technical report, right? And so being able to take your simulation results and describe what's happening in the results is a very important skill, and honestly a skill that is, you know, very poorly trained, you know, not just here, but kind of everywhere. Okay. Okay. So for CFD, you know, kind of the expectation when you kind of report on CFD results is that you have to be able to describe any notable features in the flow. Okay. So some questions to consider. So one thing that you can describe is, you know, you can describe the general path that the flow will take in the simulation, right? And so this usually is accompanied by the contour plots of the velocity and pressure fields, as well as the velocity glyphs, right? So that's about as far as we took it in activity 1. Now I want you to kind of take it a step further, not only to just show the plots, but actually describe what's happening, right? So let me give you an example. Right. So luckily, you know, for this activity, the very first image in the activity, this would be like an image of the flow, right? And so you can see here that we have the arrows that point the direction of the flow. We have the flow that's coming in from the left at the inlet and then going around to the right at the outlet, right? But along the way, we have some very kind of interesting kind of flow patterns here, right? So because of the blockage, we can see that the flow comes in and hits the blockage right here. And so we have what's called a stagnation point right here. Right? So if you remember that term from your fluid mechanics course, the stagnation point is when basically the velocity is at a minimum or at 0, hence it's stagnant. Right? And so that's definitely one feature that you want to explain in the flow, right? So the way that I would describe this is that, you know, flow comes in at the inlet with a constant velocity in the x direction. It reaches a stagnation point at this location here, right? And you can define exactly where that location is. And then you can then describe the flow then must go around it, right? Now, some of the other features of the flow is that the flow would have to kind of bend around this curve right here, right? And then it's trying to bend to the contours of the channel, right? But you can see here there's a lot of kind of empty space in the channel too, where not a lot of flow goes into. And you can see kind of we have these kind of circulating flow patterns here as well, right? So these are what we call vortices or vortexes, right? So that's another feature that you would want to explain in the flow as well, that, you know, several vortices are forming usually in the spaces where the majority of the flow is not happening, right? So we have a vortex here, vortex here, vortex here in the corners. You can see not a lot of flow is filling these areas here, right? That would be another thing that you can describe as well, okay? One other thing that you can describe about this flow is kind of where the flow kind of gains velocity and where it kind of slows down, right? So you can see here that as the flow gets to the outlet, right, we have a lot more kind of red arrows here, and the arrows get a lot bigger. showing us that the velocity is kind of really speeding up at the outlet, right? And the reason for that could be that, you have these two kind of distinct jets here that are kind of converging into one, right? And so they're all trying to kind of squeeze into this kind of small area, causing kind of an increase in velocity there, okay? So, if you're going to be doing work with CFD, you're going to be doing work with finite elements, you have to kind of really get into the practice of, describing kind of what you should be seeing, right? Because, think about, if you can kind of go back in time a little bit, think back to Monday, right? The very first thing that I showed you when we did this activity was this image here, right? But I didn't really explain anything about it. And so, if you can kind of think about, how lost you felt, or maybe you didn't feel lost, maybe you just know exactly what's going on. But oftentimes when you look at a picture like this, right? They say a picture is worth 1,000 words. And so, but oftentimes those 1,000 words are not important. And so you have to describe to your reader, which parts of this image are actually important for them to look at. Okay. Okay. So that's problem 1A, right? So I basically gave you a list of questions to kind of describe or to kind of help guide your description, right? And so you can see question 2 here is that, is there a stagnation point in the flow? If so, where? What is the maximum velocity? Where does it occur? Where is the maximum pressure, right? Generally for internal flows like this, pressure differences are driving the flow. So you should see the flow going away from areas of high pressure to areas of low pressure. Are there any areas of recirculation or vortices that result from the simulation? Where do they occur? And does this make sense? Okay. So these are kind of the questions that you should kind of be thinking about whenever you're viewing your CFD results. And these are the kind of questions I expect you to kind of answer, when you do your final project. Okay. So I'm also kind of on a sidebar. I am working on your guys' final projects right now. It will be an open foam project. And so you will be doing a simulation in open foam. And so just by that token, you should be able to describe your results. Okay. So problem 1A of this activity here kind of gives you your first chance to kind of practice what that actually means. Okay. Okay. Problem 1B. So if you had a chance to kind of finish everything with the boundary conditions, you might have noticed that it might take you several tries to get you a successful simulation because the simulation might diverge because you might have a Courant number that is greater than 1. Okay. So, part B just asked, if you had to run multiple times, how did you fix the Courant number? Maybe you didn't. Maybe you were able to get a success on the first try. And so in that case, you can kind of just mention in part B that you got a success on the first try. Okay. Part C is asking you how long did your simulation take? So that's just in physical time. So, just from the time you hit foam run until the time where the results came in, just how much time had passed, right? So the activity, it actually shows you, OpenFOAM will actually tell you how long it took. Just kind of report that in your report here. That one's a bit more for me, just to kind of just gauge how strong your guys' computers are, just so I know just how much to kind of assign for your final project. So I don't want you guys waiting for hours for simulations on your computers. So that's more just kind of for me. And then part D of problem 1 is asking you what is the Reynolds number for the flow. Okay. So Reynolds number, is very important for fluid mechanics just in general. So anytime you do any kind of, simulation or experiment work with fluids, someone always will ask you, what is the Reynolds number of the flow if you haven't done so already, right? And so part D, I want you to compute the Reynolds number, and I want you to kind of state whether the flow is laminar or turbulent. Okay. Okay. So that's problem 1, but I would say problem 1A is probably the most important part of this activity. Okay. Any questions on that part of the activity? Yes.
I know we just kind of touched on it. Everyone's gonna be different, but how much time should we expect, or should we give the computer to run this simulation?
So for the default mesh, I think the default mesh has about 40 mesh cells per direction. It shouldn't take longer than, I would say, 3 or 5 minutes. This is still a fairly light simulation. So if it's taking longer than that, then let me know. Yeah. Okay, problem 2. So problem 2 is all about increasing our capacity to do post processing. Okay. Now, besides problem 1A, right? The only kind of result that I've had you guys show so far in your CFD simulations are the contour plots for velocity and pressure. Okay. So those are great. Those are fine. You're always going to report those with any kind of simulation. But the issue with those contour plots is that they are purely, I would say, qualitative, right? So you can only really tell just based on the differences in color. So high velocity is red, low velocity is blue, right? But it's not exactly great for quantitative analysis, right? So for example, I'm going to go back to the figure up here, right? So from this figure right here, we can tell where flow is high, where flow is low, just based on the colors, based on the size of the arrows. But that doesn't exactly tell us, exactly, if we were to ask, what exactly is the velocity right in the middle of the outlet channel, right? This plot, it would be very difficult to determine that, even if we were to have the legend there with us. Okay. So this was actually a point that took forever to kind of drill into me, and my PhD advisor literally kind of had to hit me with my computer to fill it in. A color contour plot by itself is not strong enough for your results. So you also need to show some quantitative results as well. Okay. Because that's kind of the whole point of running the simulation, is that all of these numbers are in the computer, and so you have to find a way to kind of display them and kind of report them. Because otherwise you're not doing science, you're just making art. That's exactly what my advisor told me. Okay, so problem 2 is kind of the first, I would say the most basic way to kind of get some quantitative results from a simulation like this. Okay. So one very easy way to get quantitative results is to create line graphs from your simulation outputs. Okay. Okay. So what that basically means, okay, so I kind of wrote a tutorial here just based on activity 1, but you'll be expected to do this on activity 2. Okay. And so the way this works here is that if you have your domain, right? And oftentimes we want to find out what are the values of velocity, what are the values of pressure if we were to follow a particular path down the domain. Okay. And so let me see if I can draw on here just to kind of make it work. Actually, let me actually jump into the notes here real quick. Okay. So for instance, right? So actually, let me draw our channel. Might be a bit easier to see. Right? So in activity 2, right? We have our channel, which is just like this, right? We have our color contour plots. We have our velocity, our pressures. It all looks beautiful, looks great, but it's not strictly quantitative analysis, right? So one way we can do quantitative analysis is, let's say that if we followed a path, like let's say if we walked from the top of the domain here, right? So we start here, and then we walked down this path along the domain here. Okay. Right, so we're basically kind of traversing kind of through our domain. We want to ask ourselves, what are the values of pressure at every point along that line? Okay. So what we can do at that point is we can actually plot it, right? Because we have kind of a one-dimensional path, right? So that can form our horizontal axis. And then we can plot the values of pressure on the vertical axis, right? So we can form a plot that's just like this, right? Where on the horizontal axis, we have the distance along the path. Okay. And then on the vertical axis, we can basically pull the simulation results and then get the values of pressure. Okay. And then I don't know exactly what that plot would look like. Probably would look something like this, right? Right, where you can see very clearly just based on the values that are on the vertical axis, right? You can actually quantitatively tell very easily, when you're at this location in the mesh or in the model, exactly what the pressure is. Okay. So line graphs are a great tool, and in fact, they are kind of a very popular way to kind of show these kinds of results, and they're very easy to make as well, right? Okay, so let's go back to the document here. Okay, So there are multiple ways to create line graphs in from a CFD result. You can actually compute them straight from OpenFOAM. But I actually prefer to do it through ParaView instead, just because I think it's a little bit more intuitive. There's a graphical user interface there. You don't have to fiddle with the command line stuff. So all of this is from ParaView. Okay. Okay. So from the ParaView interface, there is a particular feature that we want to use. It's called plot over line, right? So the button for it is here. Okay. Okay. And then the way this works is that basically you're going to define a starting point for the line and an ending point for the line as well. Okay. And you define the X, Y, Z coordinates for those, for those different points. Okay. Okay. And another thing that may be useful for you, if you're not sure exactly kind of where those coordinates are, you can display the coordinate axes. And so there is an option within ParaView to actually display the axes grid. Okay, so I would definitely recommend highlighting that option there. Okay. Okay. And then once you define the starting point and the ending point, you can then define, which variables that you want to show. Right. And then ParaView will then make a plot for you. So then, for this particular location here, for this particular simulation, this is from activity 1. So, don't expect to get a plot like this. You can see here that we've plotted the magnitude of the velocity as well as the magnitude of the pressure. Okay. Okay. From then, you can basically save the results out. So you can save it to a CSV file, which is essentially a Microsoft Excel file or a spreadsheet. And then you can then plot it using a spreadsheet tool. Okay. I would prefer that you plot these in a separate spreadsheet program just because the plots will be a little bit more clean. You can make your own titles and axis titles and things like that. Don't just give me a screenshot from ParaView. I only have this here just to kind of show you what you expect to look like. But when you're reporting this on your report, on technical reports, I would like you to make your own plots. If you feel more comfortable, you can use MATLAB to make a plot as well. I know a couple people have asked about Python as well. You can use Python to make a plot too, but use something else other than the built-in ParaView to create your plot, just because it'll look a lot cleaner. Okay. Okay. So for this particular activity, I want you to plot the result along 2 different paths. And so one path is going to be that leads straight from the origin up to the stagnation point. And so that is from 0, 0, 0 to 2, 0, 0. Okay. And then another path I want you to plot the results on is a kind of a vertical slice through the channel, which goes from 1.5, 1.50 to 1.5, negative 1.50. Okay. And I want you to plot basically four results per line. So the X component of velocity, the Y component of velocity, the velocity magnitude, as well as the pressure. Okay. So for problem 2, you should have 8 line graphs in total. So 4 line graphs per path. Okay. All right. All right. Any questions on problem 2 of the activity? Yes.
So you said so each individual one?
Yes.
Okay.
Yeah. Yeah. So there's 2 paths, and then for each path, I want you to compute or plot a line graph for X velocity, Y velocity, velocity magnitude, and pressure. Yeah. Okay, so that's problem 2. Problem 3 is the most fun one. Well, it depends on if you want to, how much you want to blow up your computer. But problem 3 is what's called a mesh convergence test. Okay. Now, mesh convergence test. This is also, I would say, a very it's almost a requirement at this point if you're ever going to write any kind of technical report on simulations. Whether it be finite elements, CFD, what have you. Okay. Because one thing that's known, and one thing that we've talked about in this class is that when you're doing simulations like this, we are basically just approximating the governing equations, right? And that approximation or that result is actually sensitive to the size of your mesh elements. And so generally, the smaller that you make your mesh elements, or the smaller you make your mesh cells, the more accurate your results are going to be, or at least that's the expectation. Okay. And so mesh convergence tests will basically allow you to kind of quantify exactly how accurate your simulation is relative to the number of elements. Okay. So for problem 3, I basically want you to rerun the simulations. Okay. I want you to pick a particular quantity of interest. So this could be, maybe the maximum pressure in the simulation, or maybe the maximum velocity, right? So pick one metric, and I want you to plot its convergence as you change the number of cells. Okay. So the expectation for problem 3 is that you produce a line graph like this, where on the horizontal axis you have the number of cells. Each data point on this test right here is a different simulation, right? So typically you start on the left-hand side of the mesh convergence test with a very coarse mesh. And then each time you run the simulation, you're going to make the mesh more and more fine. Okay. So for this one, maybe you start with a simulation that's maybe 10 by 10, so maybe 10 cells by 10 cells per block. Don't start with 40 by 40. If you increase from there, your computer will blow up. So maybe start with 10 by 10, then go by 20 by 20, 30 by 30, 40 by 40, 50 by 50, 60 by 60. I probably 100 by 100 is probably as far as I would push it. You can kind of gauge your computer and kind of see how it's doing. But if the 40 by 40 test is already taking you 20 minutes, then don't do 100 by 100. It's going to be, you're going to have a bad time. Okay. Yeah. I would rather not send anyone else to Micro Center this for the rest of this semester. But push it as far as you can. So start with something very coarse. You could even go 5 by 5. So 5 by 5 I think is even fine as well. So start with something very coarse and just gradually kind of increase it. And then what you should see, hopefully, is that you'll reach a certain point when the results should converge, right? So the plot should plateau out. And so what that tells you is that you've reached a point where you can, if you increase the mesh, it's not gonna lead to an improvement on the solution. And so that's the ideal. Okay. Okay. All right. So for this one, I want you to run at least 5 tests, just to kind of get a good amount of data points for the mesh convergence tests. And I want you to report that for this activity. Okay. So there's quite a bit more to do with this activity than activity 1. Luckily we did a lot of the simulation part last time on Monday, but there's a lot more post-processing and analysis I want you to do. Okay. So from this point forward, so for activity 3, activity 4, and your final project, definitely expect to have these be a part of it. Okay. Question, yes.
Just a quick question on part A, where we're asked if we need to modify the time step. Do you mind showing just real quick where we used to do that?
Oh, yeah, great question. So the control, the time step size, we kind of skipped over it on Monday, but there is another file called control dictionary. Yeah, so in control dictionary, there is a parameter there called time step size, or DT. I forget exactly what it's called. And then you can change the size of the time step there. Yeah. All right. Any other questions on just the remainder of this activity? Okay. All right. I'll see kind of where everyone is. Maybe by the end of this week, I may push this due date back. Just because I do want to finish homework 5 before the midterm. And we're not going to do open foam activity 3 until after the midterm anyway. So we may push this back until then. Okay. Okay. All right. So that's good. So let's go back to our notes here. Okay. Okay. All right. So a little bit of whiplash today, but we are going back into the theory. Okay. Okay. So, question in the chat. So when is the midterm? Midterm is 2 weeks from today. So midterm is Wednesday, April 22nd. Yeah. All right. So the last major section of theory that we're going to go over in this class is time marching. Okay. And specifically, this is the technique that we're going to use to deal with unsteady problems. Okay. Okay. All right. So hopefully one thing that you guys have noticed throughout this class is that we've slowly kind of been building up each component of the Navier-Stokes, right? Because CFD, all it is, all CFD really is just we're solving just the Navier-Stokes equations. there's this one equation that we're trying to solve. You know, the only problem is that that equation is probably one of the hardest equations to solve in all of applied science, right? So let's write out the Navier-Stokes equation again, just to kind of remind us what all the terms are. Okay. This will also be kind of a good trip down memory lane just for the past 3 months or so, just to kind of see, you know, just kind of show you how much we've done in the class so far. And I'm just going to write the 2D version here. Okay, so there's our Navier-Stokes equation in all of its glory. Okay. Right. So we've dealt with actually the majority of the equation at this point at various times throughout the class, right? And so, you know, probably the first thing that we did was we tackled the second derivative term. So these are the viscous terms, but we learned how to simulate this or how to model this when we went over diffusion. Okay? Right, so that was kind of the very first thing that we did. So we did diffusion in finite differences, we did diffusion in finite volumes, and we, you know, that was kind of where we kind of started our journey of these, you know, simulation CFD results. Okay. Next one that we did, kind of almost in parallel with diffusion, was the convection terms, or the first order derivatives. Okay. So just like diffusion, you know, we also, you know, discretize convection with finite differences, finite volumes. Now, granted, we only did linear convection, but, you know, and you know, we're not going to go over nonlinear convection in this class, but, you know, I would say, you know, you guys have the bulk of the understanding of how convection works. Okay. We also did this one kind of right alongside diffusion convection. This was our source term, right? Now, the only source term or the only field term that's in Navier-Stokes is gravity. At least that's the one that's kind of mostly relevant, but it acts as a source. Okay. So all of that we did before the first midterm. Okay. After the midterm, and actually the week right before we left for spring break, we learned how to deal with this one. Right. So this was our pressure term. And so this was actually the subject for homework 4, which you guys are working on right now. And remember, the way that we dealt with this is we needed to have some kind of pressure, you know, pressure coupling equation, or the simple method is what we used. Okay. All right. So most of the gang is accounted for. The only one that we haven't dealt with yet is the time derivative term. Okay. So this is our unsteady term. Right. And it's very unique. It's the only term in our equation here that has a time derivative. You can see everything else actually is a spatial derivative, either derivative in x or y, right? And the fact that this has a time derivative means that we do have to treat it differently, right? And that's kind of why I saved it for kind of the very end of the semester, just because, you know, everything else kind of goes together. So we are going a little bit out of order than I kind of originally had planned. And so if you're kind of following the numbered lecture notes, you know, we are kind of going back in time a little bit. I think this is lecture notes 8. But I think just with how the class and how the semester has progressed, I think this kind of makes the most sense. Okay. Okay. All right. So why is the unsteady term so interesting? Right. So first of all, the unsteady term basically tells us that, you know, fluid velocity and fluid pressure, these are things that can change with time. right? So that makes perfect sense, right? So there's no flow situation that's perfectly static. So we have flow that's changing in velocity all the time, right? Even in this room, you can kind of hear the flow, sounds like the fan of the projector turned on. So that changed kind of the amount of airflow that's in the room itself. And so that's a great example of our flow changing with time. Okay. Now time is very interesting because time is what I call kind of a causal variable. It behaves very differently than space because with time, right? Time can only progress in one direction. It can only go forward in time. And so in order for us to know what happens next, we have to know what happens right now. Okay. Right. It's not something that we can kind of jump too far ahead, right? So we can only really solve things kind of one step. Time must be solved kind of one step at a time. Time is so interesting because I think there's so many different, like if you look into if you're into science fiction at all, or if you watch any of the Marvel movies, you know that there's a lot of theories about how time travel would work if it were a real thing. And so there's a lot of a lot of jokes that come with it. So you can say that you can go back in time, you can just change the position of this bottle a little bit, and then all of a sudden calcium Fullerton doesn't exist anymore, right? It doesn't quite work. I mean, I think no one really knows exactly how that would work, but it does affect how we kind of solve our systems, right? Whereas with space, right? So if you think about the way that we discretize space, we formed a single kind of linear system that kind of described how our solution behaved at all points in space, and we solved that all simultaneously. Okay, that can happen with time because with time we have to solve it kind of one step at a time. And so that kind of necessitates the development of a new set of techniques, which we call time marching. Right. And so this last section of the class is all about kind of describing what time marching techniques are, and kind of how they exactly work. Okay. Okay. All right. So that's kind of the motivation, and that's kind of the definition of what time marching is. Any questions on this so far? Okay. So before we get into the details of time marching, let's talk a little bit about notation, and let's talk a little bit about kind of what our expectations are going to be. Okay. Okay. Okay, so let's talk notation first. And so, by introducing a new variable, we have to have a way to kind of keep track of it in our solution. Okay. Oh, I guess first thing I should note that, when we're developing this theory, we're not actually going to be working on Navier-Stokes anymore, just because Navier-Stokes gets a bit crazy with a simple algorithm. So we are going to go back to our general conservation equation. going to bring back our old buddy phi. Okay. So if you remember a little bit about our notation for phi, right? We had an index for phi that told us where its spatial location was, right? So if you recall, right? So let's think about a two-dimensional case, our equation in two-dimensional space, right? We had an ij notation that told us which or where this value of phi was located in that space, right? So for instance, right? So let's say we have our 2D domain here, and let's say that we're looking at the location here, right? So the I index kind of told us kind of where the position of our phi value is, where its horizontal position is, and the J index kind of told us kind of its vertical position, right? Hence we did phi I underscore J, or we also gave just unique ID, right? The big upshot here is that the physical position of the or the physical location of our solution was always put in the subscript of our phi, right? Now for time, we need a way to kind of keep track of when in time our solution is taking place. And so to do that, we need to introduce a new notation, right? And that new notation will be in the superscript, okay? And the superscript here, this here is our time index. Okay. For these two here, I call these the spatial index. Okay. So kind of the unfortunate thing with time marching is that the notation does get a little bit messy. And so we have multiple indices to kind of keep track of, and you kind of have to keep track of exactly kind of which index refers to what. But that's kind of where we're going to stand. Okay. And in particular, there are two very specific time indices that we need to kind of keep track of as we're developing our theory. Okay. All right. So what you'll see is that as we're developing the equations, I'm going to refer to two very kind of specific times in our theory. Okay. So when something is at time index n, okay, time index n usually is used to refer to the current state of the solution. Okay. So n is used to refer to whatever is happening right then. Okay. And for all the theory that we're going to develop, we always assume that the current state of the solution is known. Okay. Right. So whatever is happening now, we know it because it's happening now. You can observe it. Okay. But in time marching, we're all about, we need to not only know what's happening now, but we need to make a prediction of what's going to happen next. Okay. So the next time index that we're going to be referring to is n plus 1. Okay. Right. So n plus 1 is the state of the solution in the next time step. Okay. And since it's in the next time step, this is something that is unknown. Okay. In fact, for all the time marching algorithms that we're going to go over, we aim to solve for the solution at time index n plus 1. Okay. Okay. Good. So at every stage of our time marching, there's going to be a known part of our solution that we know and an unknown part of the solution that we're going to solve. Okay. All right, and then we're going to denote that with the superscript index on our solution variable. All right, any questions on this so far? Okay. All right, so next thing I want to mention here is the nature of our solutions. Okay. Now, since our solution here is going to be changing with time, right? That means our the way that we view the solution, the way that we think about the solution is going to change as well. All right, and you may have already gotten a sense of this just because we've done a couple open foam activities, right? And so you kind of had a preview of this, right? Even though we haven't really done anything. So before, I would say that our solutions that our simulation that we've been running, all the theory that we've been doing have all been static, right? So they have not been changing with time. And so for a static simulation, right, essentially the entirety of the simulation could be summed up with a still image. Okay. So in the two open foam activities that we've done so far, right, I've just had you guys take screenshots from pair review, right? Because that's all there really is. So because the boundary conditions aren't changed with time, nothing's really changed with time. So a still image is enough to kind of capture all those things, right? Just like if you were to take a picture of a static object here, right? If I were to take a picture of this computer screen is not moving or changing with time. It's a static object, right? But if we were to consider unsteady conditions, those are changing with time. Okay. Right. And so think about how would you kind of record and how would you capture something that changed with time? You can't do that with a still image because a still image doesn't move unless you live in Harry Potter, right? So the only way to capture that is with a movie or a video or a GIF or a GIF or whatever, however you want to describe it. Okay. So this part's really cool, and I think this is the part I think people get excited about with CFD is that you can actually make animations from your simulation results. Okay. You might have already kind of seen this, or you might have kind of already kind of gotten a taste of it, because if you kind of been paying attention during pair review, right, in the top right corner pair review, there's that kind of there's that play button, there's that the place where we can kind of skip ahead through the frames. Now we haven't done much with it. All we've done is just kind of skip to the end, just because we're only just running a steady simulation. But in activity 4, we're going to do an unsteady simulation, and you can actually form an animation from that. And that's something that you can report. Okay. Okay. I don't know what happened with my thing here. There it is. Okay. All right. Any questions? Any questions on this so far? Okay. All right. So for the rest of the class today, I'm going to introduce our first time stepping technique, which is called the explicit Euler method. And then we may have time to start an example, but we'll probably finish it up on Monday. Okay. Okay. So let's go over explicit Euler. Okay. So the interesting thing about time stepping is that there are lots and lots of different methods for that developed in the literature. In fact, it's still kind of a topic of research. Not too many people are looking into it, but some people still are looking into more methods. But explicit Euler is probably the simplest and usually it's the first one that people learn. Okay. And the application is actually very simple. So for this, so for explicit Euler, all we're going to do is we're going to apply a finite difference approximation for the time derivative. In fact, it's just going to be a forward difference. Okay, so let's kind of see how that goes. And so let's develop this theory using our 1D convection diffusion equation, just to kind of keep things simple. All right, and this is going to be the unsteady version, so we're going to add a time derivative there. So we have partial phi partial t is equal to minus u partial phi partial x plus k partial squared phi partial x squared plus source term q of x. So it's been a while. I think we haven't seen this equation since before the first midterm. All right, so first thing we're going to do, let's use finite differences just because it'll be a little bit simpler. And let's discretize the convection and diffusion term just using basic central differences. Okay. I'm going to leave the time derivative alone for now. That'll be kind of the last thing that we do. But first thing is we have minus u. We're going to assume that we're going to be stable here, so we're not going to worry about the Peclet number. All right, so time derivative, we have phi I plus 1 minus phi I minus 1 divided by 2 delta x plus k. Then we have our central difference scheme for the second order derivative, which is phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x squared. Okay, plus q of x I. Okay. Okay, good. All right, so now that we have our spatial derivatives taken care of, let's take care of the time derivative. So for explicit Euler, we are just going to be using a forward difference scheme in time, okay? So let's apply forward difference. Okay. Okay. But the important thing is that we're doing it in time. So we're advancing not the space derivative, right? So we're not advancing the subscript. We're going to advance the superscript. Okay. Oops. Okay. So this one here is going to be phi I n plus 1 minus phi I n divided by delta t. Okay. So we applied a forward difference scheme in the time domain. So where we're making kind of our step is in the superscript, not in the subscript. Okay. Right-hand side's all going to stay the same. So we're going to just bring everything down just like before. Okay. All right, so one thing you should notice is that on the left-hand side, right, obviously we have our time stepping, we did our forward difference in the end, right? So we have n plus 1 minus phi n, right? But for the space component, notice I've evaluated both of those phi terms at the index I, right? So we have phi I minus phi I, right? So typically, when you're doing these derivatives, when you're doing these finite differences, you're not going to change more than one index at a time, right? So if you're making a difference in time, that means the space stays fixed at your current location, just okay. Now on the right-hand side, we have all those other phi terms, right? We also need to assign a time index for all of these as well. Okay. So just like we assigned a space index on the left, we need to assign a time index for all of these on the right. Okay. Now the question is, do you assign n or n plus 1, right? And it's actually not a trivial question, right? So for now, we're going to do n, right? So we're going to give the current time for every one of these time steps. But, assigning everything to n plus 1 is also a viable way to think about this as well, right? But for now, we're just going to assign everything at time step n. Okay. All right, so now we have this algebraic equation. It's a little bit of a mess, but now we can take this equation and solve it for phi I n plus 1, right? Because remember when we talked about our indices, right? Time index n, those are known, right? So we know everything at time index n. N plus 1 is what we want to solve for. Right? So in this situation here, we only have one term or one phi term with the n plus 1, which is on the left-hand side. Right? So what we're going to do is we're going to take this expression, we're going to basically just do some algebra and solve for phi I n plus 1. So let me put this as the goal. Okay. Then once we have an explicit expression for phi I n plus 1, that will give us our time marching equation. Okay, so I'm going to do this in several steps here. So first thing I'm going to do, let's multiply both sides by delta t, and then I'm also going to factor out all the factors from inside those parentheses. Okay, so multiplying both sides by delta t, we get the following. Okay, so on the left-hand side, we still have phi n plus 1 minus phi at n is equal to minus u delta t divided by 2 delta x times phi I plus 1 minus phi I minus 1, both evaluated at n, plus k delta t divided by delta x squared multiplied by phi plus 1 at n minus 2 phi at n plus phi minus 1 at n plus q at xi multiplied by delta t. Okay, good. All right, so next step, obviously we need to add phi I and n to both sides. But what I'm also going to do is I'm going to group the like terms. And so, right now we kind of grouped it according to the convection diffusion term, just to kind of make things convenient for us when we're doing problems. Let's group the like terms according to the spatial index. We're going to add bi and n to both sides. Okay. Then group like terms. Okay, and then that's the last step in the derivation. So after we do this step, we will get our explicit Euler time marching equation. Okay, and so on the left-hand side, we have phi n plus 1 is equal to, let's do phi minus 1 first. And so we have u delta t divided by 2 delta x plus k delta t divided by delta x squared, phi minus 1 at n. Okay. Plus, next, let's do phi. So phi, we just have two factors here. So we have 1 plus k delta t divided by, or 2k delta t, excuse me. Sorry, it should be minus. 1 minus 2k delta t divided by delta x squared, phi at n. Plus, you have our phi plus 1 term. So you have a minus u delta t divided by 2 delta x plus k delta t divided by delta x squared, phi plus 1 to the n plus q at xi delta t. It looks scary. I know there's a lot of terms here, but you'll see that once we actually start plugging in, it becomes straightforward to kind of use this guy. So this right here is our explicit Euler time marching equation. Okay. Any questions on the derivation so far? Yes. So the negative in front of you is for the I plus 1 term right here. Oops. Yeah, so that term has the negative because it's because we have this negative out in front here. So that negative distributes here. So that the I plus 1 term is negative, but then the I minus 1 is positive. So that's why the I minus 1 is positive. And yeah. No, for sure. The negative's confusing, for sure. When I saw that message pop up, a little bit of panic set in my head, like, did I do the negatives correctly? Because I always miss a negative somewhere. Yeah. Okay. All right. So last thing we'll do today, let's do an example. Keeping me on my toes. Okay. All right. So let's do an example to see how this all works here. Okay. So let's do very simple. Let's just do a unsteady diffusion equation. Okay, so for the unsteady diffusion equation, we are not going to have any convection. So our equation is partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. Okay, we have our boundary conditions. Our boundary conditions are also going to tell us the extent of our domain. So our boundary conditions is phi at x is equal to 0, and at all times t is going to be 1, and 2. We have a Neumann boundary condition on the other side. So partial phi partial x at x is equal to 1 for all time is equal to 2. Okay. We have just very simple constant boundary conditions here. Okay. One thing that's new here, right? Since we are going to have a condition that's going to change with time, we also need initial conditions as well. Okay. Now, this is something that we've also seen in OpenFOAM. We've mostly glossed over it, although I think I may have mentioned it in activity 1. But remember when you were setting your boundary conditions, there was a particular setting in the U and P files. We have to set the internal field. So the internal field is the initial conditions. Okay. Now, traditionally, the most common initial condition you'll see in CFD is just a simple 0, which just sets the value of solution 0 at all points. Okay, and that's what we're going to do here. Okay. So our solution at all values of x at t is equal to 0 is equal to 0. That's just the easiest thing to do. It's just easy to kind of set everything to 0 and then initialize from there. There are situations where you would want to not start from 0. If you have a particularly kind of finicky flow where it may be kind of unstable if you start from 0. But those are very, how should I say, we're not gonna see those situations in this class. But they do exist. But but for the most part, starting with 0 is a fine initial condition. It'll work for most cases. Okay. Okay. Let's also define our grid spacing as well as our time step size. So our grid spacing So our grid spacing, remember, is delta x. Let's say that is 0.25. We also need our time step size, delta t. Let's say that is 0.1. Okay. Okay, good. And so what we want to do for this problem is we want to first we're going to write out the explicit Euler time marching equation. Okay. So that's part 1 of the problem. So all we're going to do for part 1 is we're going to take the parameters of this problem and plug it into this equation up here. Okay. Right. So that's fairly straightforward. That's just kind of plug and chug. Right. Second part of this problem is we actually are going to advance the time stepping by 3 steps. Okay. So part 2 is going to solve for the first 3 solutions in the time march. Okay. So the first one is already given to us, and so the initial condition that already is one of the solutions, and so we're going to basically advance the solution 2 times in time using our explicit Euler equation. Okay. Okay. All right, so fairly straightforward problem. A lot of it is just kind of plugging and chugging and just applying our solution here. Okay, so let's go ahead and get started with that. So let's start with the first one. Okay. So part 1. Let's define all the other parameters that we have here. So besides the grid spacing and the time step size, the other parameters that we need for our explicit Euler is the convection velocity u, as well as the diffusion constant k. Okay. Now we can read those directly off the problem. Okay. So first off, we should notice that there's no convection term. And so since there's no convection, u is equal to 0. Okay. And the other thing we notice is that our diffusion constant is 3. Okay. Okay, so combining these two facts together with what we know about the grid spacing and the time step size, let's go ahead and plug all 4 of those into this expression up here. Okay. So we have a coefficient of u times delta t divided by 2 delta x plus k delta t over delta x squared. That is a coefficient for phi minus 1, and then so on and so forth. Okay. So we plug all these in. Okay. What we're going to get is a very simple kind of recurrence relation for the value of phi I n plus 1. Okay. So we get phi I n plus 1 is equal to 4.8 phi I minus 1 at n plus, or excuse me, minus 8.6 phi I at n plus 4.8 phi I plus 1 at n. Okay, good. So part 1, very, very simple. Okay. Part 2. Part 2 is we're going to solve for the solution at the first three steps of the time march. Okay. Okay. Now, when I say that we want to solve for the solution, that means we want to solve for the solution at all locations within the grid. Okay. Okay, so let's go ahead and draw our grid here. So it's just a one-dimensional line here, right? We know the grid spacings. We know the grid spacing in this case is 0.25. Okay. And we are in a finite difference scenario here. So we're looking at the nodes of this grid. Okay. Okay. So this is I is equal to 1, I is equal to 2, where the spacing in between here is 0.25. Okay. Okay. So even though it didn't explicitly say in the problem, we are going to have 5 grid points here because we know the length of our domain is 1, right? We learned that from the boundary conditions, right? So the boundary condition told us that the rightmost boundary is at x is equal to 1, right? So that's the upper bound for our values of x. And since we know the grid spacing was 0.25, that means we need to have 5 grid points in order to span our domain. Okay. Okay. So that means for every time step, we're going to have 5 different solutions. One at I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. Okay. Okay. So first, let's solve for the solution at t is equal to 0. Okay. So at t is equal to 0, okay, we're going to have 5 solutions. So 1 at each grid point. Right, so we always start at t is equal to 0. That's always our first start. Okay. Okay. So our time is equal to 0 is easy, right? So at time is equal to 0, these are our initial conditions. Right? Technically, we haven't done any time marching yet, just because we have to start from somewhere, right? And since we set a 0 initial condition, that means our solution at all values of I is going to be 0. Okay. Right? So phi I, or phi 1, excuse me. Phi 1, phi 2, phi 3, V4, V5, they're all equal to 0. All right. But you might be saying, wait a minute, right? So that seems a little bit too easy. And so on the one hand, it's supposed to be like that. So, don't stress too much. But we also have our boundary conditions that we need to obey as well. So not only do we have our initial conditions, we also need to make sure our boundary conditions are always satisfied as well. Okay, so we are going to change a couple of these just because we need to satisfy those boundary conditions. Okay, so our two boundary conditions in this case is that we have a Dirichlet boundary condition at x is equal to 0. So that we're saying phi at x is equal to 0 is equal to 1. Okay. So that means phi1 here is not going to be 0. It's going to be 1. Okay. Okay. So that's very easy. The other boundary condition is that on the right-hand side of the domain, we have partial phi, partial x is equal to 2. Okay. And so just like we typically do, we're going to form a backward difference from here. Okay. So you have phi5 minus phi4 divided by delta x is equal to 2. Okay. All right, and so if we solve this, we can say that phi5 is equal to 2 delta x plus phi4. Okay. And so we plug in for this. So phi4 in this case, so this would have to be phi4 at time index n, because it has to be something we know, right? And technically this is phi5 at n plus 1, right? And so we plug in for this, we know that phi4 at n is 0. 2 times delta x is 0.5. Or delta x is a 0.25. So that means 2 times that is 0.5. So that means phi5 here is going to be 0.5. Okay, so that's our first step there. So we did zeros everywhere except for the boundaries that we replace those with the boundary equations. All right, any questions on this before we wrap it up for the week? Okay, all right, so that's all the time we have for this week. And so when we come back on Monday, we'll continue with this example. We'll solve for the solution of the next 2 time steps, and then we'll go over implicit U. Okay. All right, so thank you guys for coming today. I know I went a little bit late today. I apologize. Hope you guys have a good rest of your day. If you have questions on the homework or questions on the open foam activity, definitely feel free to email me. But yeah, hope you guys have a good weekend, and I will see you guys on Monday. Yeah.
On exam 2, will we also be tested on upwinding techniques, or will we use?
No.
Sorry, we'll stay.
It's all, you can assume it's all safe.
Okay.
Yeah. So midterm two is only going to be on homework 4.
Okay.
Yeah. So it's going to be on the simple pressure coupling, and then
this.
stuff. Yeah. Okay. I'm thinking only 2 problems because I think first exam is a little bit longer, 3 problems.
It was long. Yeah.
Yeah. So exam 2 is going to have 2 problems. So 1 from homework 4 will be.
Okay.
Yeah. You guys did okay though. The average was right about 75%, which is it's perfect. But yeah, it was on the long side.
Thank you.
Yeah. See you guys. Have a good weekend.
Yes, awesome.